Okay, so are you ready to dive into something truly mind-boggling?
Always up for a challenge, especially when it comes to the mysteries of the universe.
Well, today we're tackling one of the biggest ones out there, black holes.
Ah, yes, those enigmatic cosmic beasts that devour even light itself.
Exactly. And get this, there's a chance we might actually be able to see one soon. Well, not see it directly, but see its shadow.
Now that's intriguing. How is that even possible?
Well, it's all thanks to this incredible project called the Event Horizon Telescope, or EHT for short.
I've heard of it. It's that global network of telescopes, right? The one that's trying to capture the first ever image of a black hole's event horizon.
You got it. And the target of their observation is none other than Sagittarius A, the supermassive black hole lurking at the heart of our very own Milky Way galaxy.
So we're talking about a black hole that's about 26,000 light years away. That's mind-bogglingly far.
It is, but that's the beauty of the EHT. It's essentially turning the entire Earth into a giant telescope.
Wait, how does that work?
They're using a technique called Very Long Baseline Interferometry, or VLBI. It's kind of like taking a panoramic photo with your phone. You know how you move it slightly between each shot, and then the software stitches them together?
Yeah, I get that.
Well, VLBI does something similar, but with telescopes and cosmic radio waves instead of visible light.
So instead of building one gigantic telescope, they're combining the power of many smaller ones spread across the globe.
Precisely. And this network includes some seriously impressive instruments, like ALMA in Chile.
ALMA, that's a big one, right? An array of 66 radio telescopes working together.
Yeah, the powerhouse. And then there's the South Pole Telescope, another key player in the EHT. Adding those to the mix dramatically increases the resolution and sensitivity of the whole system.
I can imagine. But still, to image the event horizon of a black hole that's 26,000 light years away, that's like trying to photograph an orange on the moon.
That's a great analogy and really highlights the incredible precision we're talking about here. But before we get too deep into the how, let's take a step back for a second.
Sure, back to basics.
Black holes. What are they really? I mean, the name itself sounds kind of scary.
It does, doesn't it? And the reality is even more mind-blowing. The idea of black holes has actually been around for centuries. Early thinkers like Jean Michel and Pierre-Simon de Laplace came up with the concept based on Newtonian physics.
Really? That long ago?
Yeah, but it was Einstein's theory of general relativity that really revolutionized our understanding of gravity and gave us a more complete picture of what black holes are.
General relativity.
Yeah,
That's Einstein's masterpiece, right? The one about how matter warps spacetime.
that's the one. It's a mind-bending theory, but it's been incredibly successful in explaining a wide range of phenomena, including the existence of black holes.
Okay, I remember learning a bit about it in school, but to be honest, it always seemed a bit too abstract for me.
Hmm.
Can you give us a quick refresher on how matter warping spacetime actually leads to something like a black hole?
Sure. Think of it this way. Imagine a bowling ball on a trampoline. It creates a dip, right? That's kind of what massive objects do to space-time. They warp the fabric of the universe around them.
Okay, I can picture that.
Now imagine that bowling ball being so heady that it stretches the trampoline infinitely downwards. That's what a black hole does.
Whoa, so it's not really a hole, but more like an infinitely deep well in the fabric of the universe.
That's a great way to visualize it. And the point of no return, the boundary around this well, is called the event horizon. Anything that crosses that boundary, even light, can never escape. It's like falling into a cosmic drain.
So that's what the EHT is trying to image. The shadow of the event horizon cast against the backdrop of the universe.
Precisely. And that shadow is key to understanding the properties of the black hole, like its mass and spin. But here's a question. If black holes are literally black, meaning no light can escape them, how do we even know Sagittarius A is actually there?
That's a good question. It's not like we could just point a telescope at it and see it directly.
We can't. But we can see black holes indirectly by observing their effects on their surroundings. It's like trying to figure out what's inside a sealed box by shaking it and listening to the sounds.
So we're looking for clues, for telltale signs that a black hole is lurking nearby.
Right. And in the case of Sagittarius A, we have some pretty compelling evidence. Astronomers have been tracking the movements of stars near the center of our galaxy for decades, and what they found is quite remarkable.
What have they found?
They've observed dozens of stars orbiting a seemingly empty point in space at incredible velocities. We're talking over 5,000 kilometers per second, which is about 1.67% the speed of light.
Wow, those stars are really zipping around.
They are, and the only way to explain those extreme speeds is if there's a supermassive object, like a black hole, exerting an immense gravitational pull on them.
So it's like an invisible puppeteer orchestrating this cosmic dance of stars.
Yeah.
Pretty convincing evidence. But is there anything else that supports the idea of a black hole at the center of our galaxy?
There is. We've also observed intense X-ray emissions coming from the region around Sagittarius A, and these emissions are thought to be produced by a superheated disk of material swirling around the black hole.
Like a cosmic whirlpool, with matter being pulled inexorably towards the center.
That's a great analogy. All of this points to a supermassive black hole lurking at the heart of our galaxy, and the EHT is our best chance yet to actually see its shadow.
So how does the EHT actually pull this off? I mean, coordinating telescopes spread across continents must be incredibly complex. How do they make sure all those signals are synchronized?
Well, they use atomic clocks, some of the most precise timekeeping devices ever invented, to timestamp the signals from each telescope with incredible accuracy. The signals arrive at slightly different times depending on the telescope's location, so those timestamps are crucial for synchronizing the data.
That makes sense. It's like having a cosmic conductor keeping all the instruments in the orchestra perfectly in sync.
Exactly. But even with those atomic clocks and all the other technological marvels they're using, there are still some significant challenges involved in making this global telescope work. For example, have you ever thought about how the atmosphere itself can mess with the signals from space?
Oh yeah, I've heard about atmospheric distortion. Even though we're using radio waves, which can pierce through clouds and stuff, I imagine the atmosphere can still cause problems.
You're absolutely right. Water vapor, in particular, is a major nuisance. It absorbs some of the radio waves coming from space, making the signals weaker and harder to detect. And to make things even trickier, it causes those signals to fluctuate rapidly.
So it's like trying to eavesdrop on a faint conversation through a noisy, crowded room. How do they deal with that?
Well, they try to choose observing sites that are naturally dry, like the Atacama Desert in Chile, where LMA is located. But even in the driest places, there will always be some atmospheric effects. So they also use some pretty sophisticated algorithms and computer models to correct for those distortions.
So it's like having a cosmic noise-canceling system that filters out the atmospheric interference and leaves behind the signals from the black hole. That's some seriously impressive signal processing.
It is. But then comes another challenge. Data management. We're talking about processing enormous amounts of data from all those telescopes, and remember, they're scattered across the globe, so the data needs to be physically transported from each site to a central processing center.
They're actually shipping hard drives full of data around the world. That seems surprisingly low-tech for such a cutting-edge project.
It might sound strange, but it's actually faster and more efficient than trying to transfer those massive data sets over the internet. It really highlights the scale and complexity of what they're trying to achieve.
Yeah, no kidding. But it also makes you realize just how much we stand to gain from all this effort. We could be on the verge of seeing the first ever images of a black hole's event horizon.
And not just any black hole, but the supermassive one at the center of our own galaxy. It would be a landmark achievement, not just for astronomy, but for science as a whole.
It's like finally being able to peek behind the curtain and see the cosmic wizard at work. So what are the big scientific goals of the EHT? What are the burning questions they're hoping to answer?
Well, it's not just about capturing a cool image. It's about probing the fundamental nature of black holes and the very fabric of space-time. It's about using a black hole as a cosmic laboratory to test our most fundamental theories of physics, specifically Einstein's theory of general relativity.
Okay, so we've talked about that circular shadow thing, but I'm not sure I fully understand how that works.
Yeah.
How can they use the EHT to test Einstein's theory?
Einstein's theory predicts that the intense gravity of a black hole will warp the path of light rays passing near it. This warping should create a specific pattern of light and shadow around the black hole, and that's what we call the black hole's shadow.
So the black hole is acting like a giant lens, bending the light from the stuff behind it.
That's a good way to think about it. The shape and size of this shadow are determined by the black hole's mass, spin, and how gravity works in that extreme environment. So if Einstein's theory is correct, the EHT should observe a shadow that matches the predictions of general relativity.
And if it doesn't?
Then things get really interesting. It could mean that Einstein's theory, as incredible as it is, might be incomplete. It might suggest there's a deeper level of physics at play, perhaps a new theory of gravity that works differently in the extreme environments around black holes.
Now, that would be a truly mind-blowing discovery. It would turn the world of physics upside down. It'd be like finding out the world is flat after all.
It would indeed. We'd have to rethink our entire understanding of the universe. But
Hmm.
even if the EHT confirms Einstein's theory, just getting those images would be a monumental achievement. We've been theorizing about black holes for centuries, and now we might actually see one.
It would be a testament to human ingenuity and our insatiable curiosity to understand the cosmos.
Absolutely. And it would show that even the most mysterious and seemingly unreachable objects can be revealed with enough determination and collaboration.
Speaking of those mind-boggling mysteries, let's talk about something that's always fascinated me. Time dilation near a black hole.
Ah, yes. One of the most mind-bending consequences of Einstein's theory.
We touched on it earlier, but can you remind me how that works? How can gravity actually affect the flow of time?
Sure. One of the key insights from Einstein's theory is that time is relative. It's not a constant ticking away at the same rate for everyone everywhere. Instead, time is affected by gravity. The stronger the gravity, the slower time flows.
So you're telling me that if I were hanging out near a black hole, time would actually move slower for me than for someone back on Earth.
That's exactly what Einstein's theory predicts. And the closer you get to the black hole, the more pronounced this effect becomes.
Okay, I need to wrap my head around this.
Okay.
So if I were watching a friend fall into a black hole, what would I see? Would they just suddenly freeze in time?
Well, it wouldn't be quite that abrupt, but you're on the right track. As your friend approaches the event horizon, you'd see them moving slower and slower, like a video playing at a fraction of its normal speed. Their clock would appear to slow down, and their movements would become sluggish.
Wow, that's wild. But what would they experience? Would they feel time slowing down?
That's the fascinating part. From their perspective, time would seem to flow normally. They wouldn't feel any different. But as they cross the event horizon, things get even stranger.
Okay, I'm on the edge of my seat here. What happens then?
At the event horizon, time for your friend essentially stops relative to the outside world. To you, watching from a safe distance, they would appear frozen forever at the edge of the black hole.
Hold on, so they'd be trapped there for eternity, frozen in time.
That's how it would appear to you. But for your friend, falling into the black hole, time would continue to move forward, though what they experience beyond that point is shrouded in mystery.
It's both amazing and terrifying to think about.
It is, and it really highlights how much we still don't know about black holes. What happens inside them? What's at the singularity? These are questions that continue to drive scientists and capture our imaginations.
I think that's a great point to pause for now. Okay, so we left off talking about how mind-bending time dilation is near a black hole.
Yeah, it really stretches your understanding of how time works, doesn't it?
Absolutely. But before we go any further down that rabbit hole, let's get back to the Event Horizon Telescope. We were just talking about the challenges of processing all that data.
Oh, right, the data. Yeah, it's not just about collecting it, it's about making sense of it all.
So once they've shipped all those hard drives to a central location, what happens next?
Well, they have to combine all that data from the different telescopes, which is no easy feat. Remember, each telescope is observing the black hole from a slightly different angle and at a slightly different time.
Right, because they're spread all over the Earth.
Exactly. So the signals have to be carefully aligned and synchronized, taking into account things like the Earth's rotation and the different distances the signals have to travel.
Sounds like a massive computational challenge.
It is. They use supercomputers to crunch all that data, running complex algorithms to filter out noise, correct for errors, and essentially piece together a coherent image from all those fragmented signals.
Wow, so it's like solving a giant cosmic jigsaw puzzle.
That's a great way to put it, and it takes a lot of time and computing power to do it right. The first image of the black hole at the center of the galaxy, M87, released back in 2019, took years of processing and analysis.
Years.
Yeah, it's a long and painstaking process, but the results, as we've seen, can be absolutely groundbreaking.
I can only imagine what the EHT team is seeing in the data from Sagittarius A. It's got to be pretty exciting for them. But before we get too carried away with anticipation, let's talk about some of the potential scientific implications of this project. We've touched on Einstein's theory of general relativity, but how exactly can the EHT be used to test it?
Well, remember that circular shadow we talked about? The shape and size of that shadow are directly related to the mass and spin of the black hole.
Right. And those properties, in turn, are determined by how gravity works in that extreme environment.
Exactly. So by measuring the shadow of Sagittarius A with incredible precision, the EHT team can compare their observations to the predictions of general relativity.
So it's like a cosmic test of Einstein's theory.
Precisely. And if the observations match the predictions, it would be another stunning confirmation of general relativity, which has already passed every other test we've thrown at it.
But what if they don't match?
Well, that would be even more exciting, wouldn't it? It would suggest that our current understanding of gravity might be incomplete, and that we need a new theory to explain what's happening in the extreme environments around black holes.
Okay, now we're getting into some serious mind-bending territory. A new theory of gravity. That would shake things up in the world of physics.
It certainly would. It would mean that there are things about gravity that we still don't understand, and that there's a whole new realm of physics waiting to be explored.
And EHT could be the key that unlocks that door.
It could be. But even if the observations perfectly match Einstein's predictions, the EHT will still provide us with an unprecedented glimpse into the inner workings of a supermassive black hole.
I mean, we'll actually be able to see how matter behaves as it's being pulled into a black hole.
Right. We'll be able to study the dynamics of the accretion disk, the superheated gas and dust swirling around the black hole, and we might even be able to detect jets of particles being blasted out from near the event horizon.
So it's not just about the shadow, it's about all the other stuff happening around the black hole as well.
Exactly. It's like getting a front row seat to one of the most extreme and energetic events in the universe.
I'm starting to understand why people are so excited about this project. But let's not forget about time dilation. You were saying how time slows down near a black hole, right?
Yes, that's one of the most mind-boggling predictions of general relativity. And it's not just a theoretical concept, it's been experimentally verified in weaker gravitational fields here on Earth.
Really? So how does that work? If I were to spend some time near a black hole, would I actually age slower than someone back on Earth?
That's exactly what the theory predicts. The stronger the gravitational field, the slower time flows relative to an observer in a weaker gravitational field. It's all about relative motion and the curvature of space-time.
I think I'm starting to get it. But it still feels kind of weird to think that time isn't absolute, that it can actually be stretched and warped.
It's definitely one of those concepts that takes some getting used to. But the more we study the universe, the more we realize that our everyday intuitions about space and time just don't apply in these extreme environments.
So, to put it simply, if I were to fall into a black hole, time would essentially stop for me from the perspective of someone watching from a safe distance.
More or less, yes. They would see you approaching the event horizon, but you would appear to slow down and eventually freeze in time at the edge of the black hole. You would never actually appear to cross the event horizon.
But from my perspective, falling into the black hole, time would continue to flow normally.
That's right. You wouldn't experience anything unusual as you cross the event horizon. But from that point on, your fate would be sealed. You would be inevitably drawn towards the singularity at the center of the black hole.
And what happens at the singularity?
That's the big unknown. Our current laws of physics break down at the singularity, so we can only speculate about what might happen there. Some theories suggest that matter is crushed out of existence, while others propose that it might be transported to another part of the universe or even to another universe altogether.
Whoa, that's some seriously heavy stuff. We're talking about the ultimate fate of matter, the very nature of reality. It's enough to make your head spin.
It is, but that's the beauty of black holes. They push the boundaries of our knowledge and challenge us to think beyond our everyday experiences.
I think that's a great place to leave it for today. We've covered a lot of ground, from the incredible technology behind the Event Horizon Telescope to the mind-bending physics of black holes. Okay, so let's pick up where we left off, exploring these incredible cosmic enigmas we call black holes.
I think we were about to delve into some hypothetical scenarios, right? Like, what if the Event Horizon Telescope shows us something totally unexpected?
Yeah, what if those observations don't quite line up with Einstein's theory of general relativity? What if that shadow isn't perfectly circular like we expect it to be?
Ah, that's where things get really exciting. It would mean that our current understanding of gravity, as good as it is, might need a little tweaking, or maybe even a major overhaul.
So we might need a whole new theory of gravity just to explain what's happening around black holes.
Possibly. It would open up a whole new chapter in physics. Scientists would be scrambling to figure out what's going on, proposing all sorts of new ideas and models. It would be a revolution in our understanding of the universe.
A revolution? That's a pretty big deal. But even if the EHT confirms Einstein's theory, those images will still be a landmark achievement, wouldn't they?
Oh, absolutely. I mean, just think about it. For centuries, black holes were just theoretical concepts, mathematical curiosities, and now we might actually have visual evidence of their existence. It would be a testament to human ingenuity, our ability to probe the deepest mysteries of the cosmos.
Speaking of mysteries, let's circle back to that mind-bending concept of time dilation. How exactly does that work near a black hole?
Right, time dilation. One of the most counterintuitive predictions of general relativity. Essentially, it means that time is not absolute, but relative to the observer's reference frame.
So the way time flows depends on where you are and how fast you're moving.
And also on the strength of the gravitational field you're in. The closer you are to a massive object like a black hole, the slower time flows for you relative to someone farther away.
Okay, so let's say I'm watching a friend fall into a black hole. What would I see?
Well, as your friend approaches the event horizon, you'd see them moving slower and slower. Their clock would appear to tick more slowly, and their light would get redshifted, meaning it would appear to stretch towards the red end of the spectrum.
Red shifted, so they'd start to look kind of reddish.
Yeah, and their movements would become more and more sluggish. Eventually, they would appear to freeze completely at the event horizon.
Frozen in time, so they'd be stuck there forever.
From your perspective, yes, they would never actually appear to cross the event horizon, but from their perspective, time would continue to flow normally.
So they wouldn't even realize they were frozen in time.
Nope. To them, they would continue to fall towards the singularity at the center of the black hole. And what happens there, well, that's still a mystery.
The singularity, the point of infinite density where all matter is crushed out of existence.
That's the current thinking, anyway. But it's important to remember that our understanding of physics breaks down at the singularity. We don't really know what happens there.
It's like a cosmic abyss, a point beyond which our knowledge simply can't reach.
Exactly. But that's what makes black holes so fascinating, isn't it? They represent the ultimate frontier of knowledge, a place where the known universe meets the unknown. And with projects like the Event Horizon Telescope, we're getting closer than ever to peering into that abyss and maybe even glimpsing something beyond.
It's both exhilarating and a little bit terrifying to think about.
Mhm.
So to wrap things up, what's the big takeaway from all of this?
I think the main point is that black holes, despite their ominous name, are not just cosmic monsters lurking in the darkness. They're incredible laboratories for studying the most extreme limits of physics, and they hold the potential to unlock some of the universe's deepest secrets.
And with the Event Horizon Telescope, we might finally be on the verge of witnessing those secrets firsthand. So stay tuned, folks, because the next few years could be absolutely groundbreaking in our understanding of black holes and the universe itself. Thanks for joining us on this deep dive, and until next time, keep looking up and keep those minds curious.